All right, so here we are into chapter 15 now on carbohydrates. It's the first real biological chemistry chapter. We hinted a little bit at this in chapter 14 when we talked about hemiacetals and acetals, and we looked at some of those carbohydrates, the disaccharides that form, and how they behave according to hemiacetal and acetal behavior. But now we're ready to full on examine a little biological chemistry here in the carbohydrate chapter. As our first lecture in carbohydrates, this first section is just a generic introduction to carbohydrates, or carbs as they're more commonly known in public. And these are important compounds, things that, as we'll see, the name gives a lot of information because there's a carbon and a hydrate, an H2O, for every unit of carbon. And people tend to love them, although they've come under fire in diets recently as being a cause for excess weight gain and other problems. So people have tried no-carb diets, and those have varying degrees of success. But like them or hate them, carbohydrates are a necessary biological fuel, and we'll explore why in this chapter. Carbohydrates are a varied group of macromolecules. They can include things like table sugar that tastes really sweet, sucrose, a disaccharide. Lactose, another disaccharide, doesn't taste nearly as sweet and unfortunately gives a lot of people some problems if you're a lactose intolerant individual, or all of us as we age have some degree of lactose intolerance. And then finally cellulose, that's neither sweet nor appears like these simple disaccharides, but is an important structural and starch carbohydrate. The thing that links all these different carbohydrates is the fact that they're made up of carbon, hydrogen, and oxygen in a ratio of 1 carbon to 2 hydrogen to 1 oxygen, or at least roughly that. For the monosaccharides, it's strictly that, and then the disaccharides, we'll see it's close to that, and polysaccharides like cellulose, approximately that. And they make up about 65% of our diet. Again, this is a normal, average American diet. Pastas, breads, potatoes, as we see in our image there. Of course, if you're on a no-carb diet, you try to restrict the amount of carbohydrate, but there's still got to be some for reasons we'll talk about in a moment. Okay, so glucose is our key carbohydrate. It's produced by photosynthesis in plants from carbon dioxide in the air, water from the roots, and then energy from the sun. And then it's oxidized in living systems through cellular respiration, ultimately to produce CO2, H2O, and energy, just what went into forming it in the first place. So we see that down below as a reversible reaction. And of course, glucose is the only fuel for the brain. So if you are on a no carb diet, well, your brain still needs that glucose and it's going to get it one way or another. And of course, it's very tough to restrict all carbohydrates in the first place, but certainly people who are avoiding carbohydrate rich foods may be getting some carbohydrate in the foods that they do consume. Now, hopefully you noticed that reversible arrow. That's a chemist's way to see something that's a cycle. We can also talk about the carbon cycle, which just takes that photosynthesis forward reaction and respiration reverse reaction from the previous slide and makes it more explicit that this is a cyclic process. This is nature's way of allowing things to go on and on and on for generation upon generation. So during the photosynthesis end, the energy comes from the sun, combines that CO2 and H2O to form glucose, our model carbohydrate, C6H12O6. So there's that 1 to 2 to 1 ratio of carbon to hydrogen to oxygen, hence the name carbohydrate. And then finally, oxygen is also produced, and that's important for those of us organisms that use oxidative respiration, because in the next step, we see that respiration in the body, carbohydrates are oxidized to CO2 and H2O using oxygen and producing energy. And so there we have the reverse process. So it's a very nice cycle. It keeps things nice and maintained in terms of balance, and it's worked really well for many, many years until humans started to get involved and started to adjust things a little bit, but still mainly the carbon cycle goes undisrupted. Now, we mentioned earlier that there's a variety of carbohydrates available, and within that variety of carbohydrates, there's three main types of carbohydrates. The monosaccharides, which are the simplest carbohydrates, things like glucose, that have that strict 1 to 2 to 1 carbon to hydrogen to oxygen ratio. And then there's the disaccharides, which consist of two monosaccharides bound together, and because those do eliminate water as they form, they don't quite strictly obey that 1 to 2 to 1 ratio, but they get pretty darn close. And then finally, polysaccharides, of course, have very large molecular weights and again approximate that carbohydrate, one carbon to an H2O roughly. But again, over those many, many units, you might have a little bit of deviation, just like in the disaccharides. So investigating the monosaccharides in a little more detail, the monosaccharides consist of 3 to 6 carbon atoms typically. They typically also have a carbonyl group, and that's either an aldehyde or a ketone-based carbohydrate, and then several hydroxyl groups. Again, we don't classify them as alcohols, but they have those hydroxyl groups in the aldehyde or ketone carbonyl group, and again, that's a special type of molecule known as a carbohydrate rather than an alcohol or an aldehyde or a ketone. Within these types of monosaccharide structures, you tend to get two types based on what that carbonyl group is. So if the carbonyl is an aldehyde, then we have an aldose, in which we have that carbonyl group on the first carbon being an aldehyde, and therefore a terminal, because it would have a hydrogen off of that. And again, that's in the chain structure, not the ring structure. For ketoses, now we have a ketone carbonyl, so the carbonyl is on the second carbon, and therefore it's not an aldose, it's a ketose because it's not an aldehyde, it's now a ketone. And again, we're talking about the ring structure, I'm sorry, the straight chain structure, although the ring structures do predominate. So here we see examples of each of those types. So you see in the left-hand case, we have an aldehyde, right? C double bond O with an H on one side and a carbon group on the other side of that carbonyl carbon. And that's erythrose, which is an aldose. If we look next to it, there's erythrulose, and that has now the carbonyl on the second carbon. So that carbonyl carbon is bonded to two other carbon groups. That's a ketone, and therefore now we have a ketose. So that's how we're able to get these two different types of monosaccharides depending on the functional group where that carbonyl is, whether it's an aldehyde or ketone. Notice that both the aldose and the ketose shown here have plenty of hydroxyl groups throughout the structure. Hopefully you caught on to this ose ending that both the aldose and the ketose had on the previous slide, erythrose or erythrulose. There's the common naming convention that they end in OSE, and they can be named according to the number of carbons as well. So we can have a triose, which would have 3 carbon atoms total. A tetrose would have 4 carbon atoms total. Pentose would have 5 carbon atoms total, and pentoses are very important, especially late in the semester when we talk about ribose and deoxyribose when we go into nucleic acids. And then finally, hexoses are what we tend to see here when we're talking about carbohydrates as fuel molecules, and those are 6 carbon atom monosaccharides. So as we saw with erythrose, we can have aldoses, which are monosaccharides that have the aldehyde functional group, and then many hydroxyl groups. Depending on how many carbon atoms, you'll have a certain number of hydroxyl groups possible. So we can have an aldotriose, however you want to pronounce that one, which would be 3 carbon atoms with the aldehyde functional group. You can have an aldotetrose, like we see there in threose on the right-hand side of the slide. That's an aldotetrose because it has 4 carbon atoms total, and it has an aldehyde functional group. That first carbon atom has the carbonyl and the hydrogen, and then a carbon group on its other side. We can have an aldopentose if we have 5 carbon atoms and an aldehyde functional group. And then finally an aldohexose if we have 6 carbon atoms and one of the aldehyde functional groups, right? That first carbon atom bearing the carbonyl. Now, in addition to the aldoses, we can also have the ketoses, and so ketoses are also monosaccharides. The distinction, of course, is they have a ketone carbonyl with carbons on either side of the carbonyl carbon, as opposed to an aldehyde with a hydrogen on one side and a carbon group on the other side of the carbonyl carbon. Likewise, just like the aldoses, you get many OH groups, those hydroxyl groups, depending on how many carbons you might have. And here we see, just like with the aldoses, we can have the ketoses with from 3 to 6 carbons commonly. So we can have a ketotriose, like we had an aldotriose on the previous slide, and that would have 3 carbon atoms. We can have a ketotetrose with 4 carbon atoms. We can have a ketopentose with 5 carbon atoms. And we can have a ketohexose with 6 carbon atoms, like the fructose that we see on the right-hand side. Fructose is a very common sugar known as fruit sugar, and it's a nice sweet sugar, and it happens to be a ketohexose. We also talked about glucose, which was another hexose, right, with that C6H12O6 formula. Well, look at fructose there. It also has the C6H12O6 formula. So that single formula, as we talked about earlier in the course, a single molecular formula can give rise to a number of different structures, and that's why those 6 carbon, the hexoses, tend to have a variety. Whether we're talking about ketohexoses or aldohexoses, they all tend to have that same basic number of hydroxyl groups, and a carbonyl, it just depends on if we're talking about a ketose where the carbonyl has carbon atoms on either side of the carbonyl carbon, or an aldose where one side has the hydrogen. And so here we see a variety of monosaccharide examples. We can have something as simple as glyceraldehyde there, which is an aldotriose, right? Ending in the word aldehyde probably told you it was going to be an aldo, and then counting those 3 carbons lets us know it's an aldotriose there. Triose, as we saw on a previous slide, that's an aldotetrose, 4 carbon atoms. And then we have the ribose, which I mentioned before, that ribose and deoxyribose are important pentoses because they're involved in RNA and DNA. So here we see the aldopentose ribose has 5 carbons. And you'll notice also that you have 1 fewer hydroxyl group than carbon. So if we go back to glyceraldehyde, it's got 3 carbons and 2 hydroxyl groups. Triose has 4 carbons and 3 hydroxyl groups. Now ribose has 5 carbons and 4 hydroxyl groups. And then finally fructose, which we had just talked about on our previous slide, has now 6 carbons and 5 hydroxyl groups. So there we have it. Again, fructose is a ketohexose, whereas everybody else on this slide is an aldose, depending on how many carbons. It gives a different number there, but looking at the structure, it's clear that fructose has that carbonyl on carbon 2, whereas everybody else on this slide has the carbonyl as carbon 1. Okay, so we've covered a lot of ground here on the basics of carbohydrates in this first lecture. Let's take some time now to see how well you're processing all of those differences. So here we have 2 structures, A and B, and for this learning check, your goal is to identify each as an aldo or a keto, and then as a tetrose, pentose, or hexose. So go ahead and put them together to give me the overall general type of monosaccharide. Please pause the video here while you complete that task and start it back up when you're ready to check your work. Good luck. Okay, so let's look at A first. If you count those carbons, that was probably the easier task to do. Although maybe if you're becoming a real organic chemist, you're also looking at those functional groups first. Either way, if we count the carbons first on A, we know we're a hexose, right? There's 6 carbons. And if we count our carbons on B, which now has 5 carbons, we're a pentose. So there we at least know how we end. Let's figure out how we start. Well, in A, we have that carbonyl group on the very first carbon, which means we have a hydrogen on one side and a carbon group on the other side of the carbonyl carbon, and therefore we have an aldohexose. That's an aldehyde functional group, and therefore an aldohexose. For B, now we've got the carbonyl carbon on carbon 2, so we have a carbon group on either side of the carbonyl, and that is a ketone functional group, and therefore we have a ketopentose. So figuring out hexose and pentose hopefully was pretty easy. You just counted carbons, but finding those functional groups told us that A is an aldohexose, whereas B is a ketopentose. Hopefully that went very well for you. If not, please do try some additional problems and certainly get in touch with me if you're having trouble with either the aldo or keto part or the tetrose, pentose, hexose, triose part of things. Okay, but hopefully things are going very well for you, and we'll see each other again in the next lecture.